Hello everyone, and let's in this video finally learn about what does it mean for a function to be concave up, concave down, what does it mean to change the concavity, and what the points of inflections are. We're also going to learn about second derivative test, and basically we're going to teach you what the second derivative tells about the function. Well, I want to use the example of COVID-19 again, since it's such a hot topic right now in 2020. And I found those graphs for different countries, how the exponential growth of the virus was going through each country day by day. So as you can see here, time t, and then we keep adding days, and we have different countries here, China, South Korea, Italy, and so on, including United States in brown color. Well, what is so interesting about that? Maybe you heard about this information before, about something like flatten the curve. What does it mean to flatten the curve? This is exponential growth. If you check how many people got sick every day, it first doesn't go too fast, and then every day it literally doubles and doubles. Because what does it mean to have exponential growth? If you imagine 2 to the n, that means it's 2 times 2 times 2 every next day. If this day you had 16 people, the next day it will be 32, and it's crazy that next day will be twice in the previous one. Now imagine if it's 5 to the n, and so on. So this is the exponential growth, and COVID-19 indeed had exponential growth in each country, which is pretty crazy. However, it cannot go like this forever. You do understand that there's not enough people in the world to keep having exponential growth for any kind of virus. At some point, either everyone will be sick and then the virus will not have place to go anywhere else, or something will happen like the isolation of all the people and we're gonna all stay at home, and then the virus will not have place to go as well. The second scenario is definitely better than the first one. So that's what they're talking about. They're talking about the point when the virus, let me still use the blue color, was growing. It was growing exponentially, and then at some point something happened here that the virus is still growing. You see the function is still increasing. The function is still increasing, but now with a slower rate. I mean, compare exponential growth, goes up super fast. And if it would keep growing like this, it would look this way, like e to the x. But instead it became like this. The function is increasing but slows down, and at some point flattens the curve. Still increasing, right? But flattens the curve. So this is what we call point of inflection, or inflection point, or POI. And that's an important thing, not only in epidemiology, the science that studies epidemics, but also in business and engineering and so on. That means growth cannot go the same way exponentially all the time. At some point, something should happen for this growth to change. Before this point, the function was increasing with the increasing rate. After this point, the function is still increasing, but with the decreasing rate. And this rate is coming from how many new sick people we have tomorrow over how many sick people we had today. So for this function, it looked like the point was over here. And then for the green one, which it seems like to be Iran, you see it was exponential first, and then, it's still growing fast, and then it's changed over here, exponential over here for Italy, and then you see, hopefully that means now it slows down, and hopefully it will go like this, and so on. Very, very natural for Korean example. Look at the Korea example in yellow. It was growing really fast up, right? But instead of keep going up over here, it seems like it starts slowing down. So here's one more interesting picture, a zoom in graph of what I'm just saying from a very good video. I'll make a link to this video. And they say that it's exactly what we call inflection point, and to find it, we want to find the growth factor. The growth factor is taking the number of sick people on a day d and dividing by the number of sick people on a day d minus 1. So tomorrow over today, or today over yesterday. And if the numbers are keeping huge, that means the exponential growth is happening, and that's very scary. Looks like this. But if this ratio it becomes smaller, then means tomorrow, if today we had 300 people, tomorrow we have 310, that's not doubled anymore. And that's exactly what we're looking for. We're looking for this point. How to have this point using government? Usually CDC is the one that steps in. If you don't know what CDC is, Google. The Center of Disease Control usually steps in and tells everyone, okay, enough is enough, everyone should stay at home or else. If everyone indeed stay at home, this point happens, and now that we still have new sick people, for example, people in the hospital make each other sick and so on, but at least not with exponential growth anymore. And this not only happens with COVID-19, but even normal flu or pox. CDC usually comes and announce those measures to make sure that we do have inflection point and exponential growth stops. Well, let's have an official mathematical definition, because I just mentioned CDC to you, and indeed, mathematicians are the ones who tell CDC when this should happen. What day is the perfect to close your school so that we can change the epidemic spread? What day is the best to close the kindergarten? And so on. We're the ones who calculate it. Mathematicians do that. CDC has a whole math modeling group which consists of statisticians, mathematicians, applied mathematicians. They use coding like C++ and Java and so on. And they actually calculate those times and give suggestions. So officially, we're gonna say that the function first of all have to be differentiable, that makes sense. And then on the open interval, then if the derivative is increasing, think about that, not the original one, the derivative is increasing. That's what I said, the speed is getting faster, right? The derivative is speed. So the original function is increasing with the increasing rate. Because this is rate, if you think about the original function, the first derivative, if it's rate. So if rate is increasing, then we call this, we call original function to be concave up on I. Now, if the derivative now is decreasing, so the function is still increasing, but with decreasing rate, right? Decreasing rate, like on this graph. It's still going up, but slower than before. So the rate is decreasing. Then we say that the original function is concave down on the interval I. If we can find the point that's changed the concavity, and let's call this point C, then from up to down, from down to up, then we call this point to be inflection point, and that's a very important thing to identify. Inflection point at C. Very good. So, I usually say that concavity is about second derivative. So that's very important to remember. Concavity is something about second derivative. Increasing, decreasing is usually something about the first derivative. Concavity is about second one. Why? Let's see why. If the second derivative is positive, then we're gonna say that the function is concave up. If the second derivative is negative, then the function is concave down. And again, if there's a point that changed the sign of the second derivative from positive to negative and negative to positive, then we call this point to be inflection point. This sounds familiar. Doesn't it remind you the sine line we had before? So it seems like now we're going to have a sine line, but for the second derivative. We're going to put points C on the second derivative sine line, and we're going to identify the sign of the second derivative. If the sign of the second derivative is positive, negative, positive, it doesn't matter, positive, negative, negative, positive. If it's positive, then the original function f in pink is concave up. If the second derivative is negative on the open interval I, right? So it's concave down. The original function is concave down, and so on. If C change the concavity, we call these points, we can have many points of inflections. So from now on, we're going to have one more sine line. Sine line for the second derivative. Sine line for the second derivative. Before we had sine line for the first derivative, and plus minus plus indicated increasing, decreasing behavior of the original function f. Now, why it's also important not only for the epidemiology and diseases, in business, actually, I want to show you that's a pretty cool idea that when you introduce a new interesting item to the market, everyone like it right away and want to buy it quite a lot. Do you remember those spinners everyone were buying like crazy? It was 2018, I think, or something like that. Well, when they just show up on the market, if you would look the graph of the profit, it skyrocketed. So it was going exponentially. Everyone wanted to have that spinner. It was so popular. So the graph was going up really fast, say exponentially fast. But then everyone had the spinner already and everyone got bored from the spinners. Well, how many spinners do you need to have fun with it? 1, 2, 5? Well, it should be enough at some point. So at some point, people realized it's not so interesting anymore. And some people were still buying it, right? But now at a slower rate. Maybe you lost a spinner and you wanted one more. You wanted to buy a present for another person, but how many of these do you need? 1, 2, or 3? You know. So this point of inflection also is widely used in business and economics. It will show you when your item you are selling is not interesting anymore. And then what do you do to avoid this slowdown of the growth? So the profit is still growing, right? You can see it. The function is still increasing. And here it's increasing, but the function is increasing with increasing rate, right? At first rate. Because everyone really liked spinners. After that point of inflection point, the function was increasing with decreasing rate. So the people who were selling spinners still had profit, still had money, but not as many as before. That is because the second derivative became negative versus it was positive. On the blue color over here, the original function is concave up, concave up, and on a pink location, it's concave down, concave down. And the point is the point of inflection because it's changed the concavity of the function and it's also in a domain. That will be an important point in the future. So to find this point is important if you plan to start some kind of business. Why? Because if you know that when people will get bored of your product, you maybe want to change something, maybe advertise some new features of a spinner, or maybe make a discount or a Black Friday and so on. For example, with Coca-Cola products, do you remember what they did? Everyone kind of got bored of it, and then they just decided to put names on the Coca-Cola bottles, and it became super popular again. So they kind of delayed the inflection point. That's a very interesting application. Now, I want to give you some interesting question over here. So if the concave up shape looks like this, and as also I will tell you the interesting way how I remember. Did you remember which one is which? Is if the second derivative is positive, it's concave up or concave down? Concave up, correct. There's a way to remember it. So I usually teach it this way. If the second derivative, so I'm talking about second derivative, is positive, then the original function is smiling, right? Looks like a smiling face. And that's exactly what we're going to call concave up. Concave up. If the second derivative is negative, then the original function is grumpy. And that's what we call concave down. Basically, one is a cup looking up and the other one is a cup looking down. You also should maybe imagine it this way. If I pour water on top of the concave down function, the water will fall. If I pour the water on the concave up function, the water will accumulate. Same over here. The water in this location will be accumulating, versus on this location over here, it will fall down. Do you see anything interesting? Seems like if original function looks like this, basically a parabola, for example, at this location in this interval, the function looks like a parabola. What is over here? What is that? Does it remind you anything? Well, it does remind you a tongue, but that's not what I'm talking about. This tongue reminds you some kind of minimum, right? And when the parabola is concave down, or just in general the function is concave down, what is this? This nose seems to be maximum. And that's exactly what the second derivative is about. The second derivative test uses second derivative to check if the function has maximum or minimum without using the first derivative test. It kind of jumps through. That's what we're going to call second derivative test. Second derivative test to find local extreme values. If my second derivative is continuous on the open interval, and I need to find those critical points. But if you remember, usually critical points are the one that not only the derivative is 0, but also the derivative is d and e. For the critical points for the second derivative, we don't really use d and e points, but they will still be important as points of discontinuities. You'll see later. So basically, find the first derivative, set it equal to 0, solve. You will get some critical points. Let's call them critical points because something critical is happening there. Then find the second derivative. Plug those points into second derivative. If the second derivative is positive, you've located local minimum. You see, positive gives you minimum. If it's hard to remember, memorize the smiley face. Positive gives you minimum. If the second derivative is negative at that point, that's local maximum, because the face is grumpy and it gives you this maximum over here. If the second derivative is 0, then the test is inconclusive and you just need to use another test. For example, the first derivative test. It might not have minimum, maximum at all, or might have any. So second derivative steps. I think it's nice if you guys have steps for that, because it's a little bit confusing. First, find f prime. Find the derivative of your function. Set it equal to 0. Solve for this c. Let's call them critical points. But they should be in the domain. Then keep them in mind, but now find second derivative. And keep the equation of a second derivative, put it in the box. Step 3, plug c into your second derivative. When you plug, you see the sign. You don't even need to know the number. If second derivative is positive, do you remember minimum or maximum? Smiley face or grumpy face? I sometimes remember it's the opposite. Positive, then it's minimum. And then if derivative is negative, then maximum. The second derivative. Those are my steps. Let's do one example. So if you're ready to keep working somewhere, you can stop and do some homework. But I want to go over this interesting example for the function f of x, which is x to the 4 minus 4x cubed. Find where? So let's do like this. Find local extrema. That's local minimum, maximum. Local extrema. Find points of inflections. Find intervals for concave up, where the function is concave up and down. I also can ask you to find where the function is increasing, decreasing, and so on. We're going to do this, all this, and I'm going to sketch the graph in the next video. Okay, so first, if they ask me to find local extreme values, points of inflections, and so on, they're talking about the derivative. Which one? Local extreme values are usually about the first derivative, but we just learned that we can use second derivative test to do the same thing. But it doesn't really matter, the first step is always the same. The first step is to find the first derivative. 4x cubed minus 12x squared. Now, if I want to perform first derivative or second derivative, doesn't matter, I still need to solve it for 0 or d and e to find critical points. Critical points. To solve something like this, I will factor out 4x squared. Always factor out x with the lowest exponent. Then I will have x minus 3 equals z to 0. So I have two roots, x is 0 and x is 3. The domain for this function, all real numbers. There is no denominator, no square roots, and so on. So both of those points can be called critical points or critical values. CVs, CPs, and so on. Critical numbers, CNs. Depends on which book you're using. Now I can choose. Which one to use. First derivative test. That means I will build the sign line for the first derivative and put my CPs on the first derivative sign line and then find plus minus, increasing, decreasing. Or I can choose to use second derivative test, which is actually faster because I don't need to have a sign line. I'm just going to plug those CPs into my second derivative to see the sign of it. And since this is a new topic, let's choose a second derivative test and see if it's faster. Usually it's faster for many applicational problems. So step 2, I'm going to choose second derivative test. Second derivative test. For that, I need second derivative. I'm going to put these critical points into the box and I will find second derivative. F prime prime is, don't use the factored form, use this one, will be 12x squared minus 24x. And now look what's going to do. I will just plug my critical points into the second derivative. So I want to know the sign of f prime prime at 0 and f prime prime at 3. At 0 it is 0, which means there is no info, inconclusive. This test is inconclusive. No info. That means use another test. Yeah, that's a bummer. That means the choice was not very good, and then first derivative test will figure this out. But we just wanted to show you that these cases happen. You should not freak out, that's fine. But look how fast it will go with the other point. F prime prime at 3, positive or negative? Well, 3 times 3 is 9. 9 times 12 is definitely bigger than 3 times 24. So I don't need to know the number. I just need to say, okay, that's bigger than 0. That's a very cool thing because sometimes intuitionally you just know the answer. And since it's greater than 0, you remember this smiley face, then it is, we can say, local, minimum or maximum. Since it's at the bottom of the smile, then it's minimum. That's how visually you can memorize it. Hello, people who like visualization. So it's local minimum. Okay, that question was answered. Third one asks to find concave intervals for concave up, concave down, and inflection points. So for points of inflections and concavity, use sign line for the second derivative, because remember that points of inflections and concavities, let me change the color, are all about second derivative. are all about second derivative. Remember that. Concavity. So I'm gonna build second derivative sine line for f prime prime, and I'm gonna put 0 and 3, those critical points I found from the first derivative. So see what we're doing with the sine line for the first derivative. We do the same thing. For the first derivative sine line, we put roots, actually not. In this case, we're using roots for the first derivative and put them on a sine line for the second derivative. Now, I want to use some test points in those intervals to see what's going to happen if one test point on this interval will show me that the function there is concave up, then the whole interval will be concave up, concave down, then concave down, and so on. So I need to find the second derivative and put it in the box. I always recommend to do it right away. And now I'll be plugging test points, so I'll write down ones for you to have nice notation. Plug test points now into second derivative, and second derivative is 12x squared minus 24x. Also, maybe it's more convenient to factor it out. 12x will be x minus 2. Actually, that's how you knew that at 3 it's positive. When I plug 3 here, indeed the second derivative becomes positive. Okay, let's choose some nice test points. And you can choose anything you like. For example, minus 1. What is happening at negative 1? At negative 1, this will be negative, this will be negative. Negative times negative, that's positive. Should it be positive or not? The second derivative is positive, yes. So I'm gonna put plus here. Now, if I choose some simple test point like 1, you can choose anything. You can choose pi if you want 1.7 and so on. Well, not pi. Pi actually should be over here. If you want pi, you can choose pi. But all those points, they should be simple to use. That's why you call them test points. It's nice to have some convenient points. So what is happening for the second derivative at 1? At 1, 1 minus 2 is negative, but times 1 is positive. 12 is positive, so everything is negative. And what is happening, say, at 10? You don't have to do 4 or 5, just anything, or even 100. At 100, this is positive, and everything is positive. Positive times positive becomes plus. Thus, I will make this kind of notation. You don't have to use it, but I like it. The original function f is concave up from minus infinity to 0, concave down from 1 to 3, and concave up from 3 to infinity. All 3 points here, all 2 points, 0 and 3, changed the concavity. That's why, and since they are in the domain, that's important, we can call them points of inflections. Note, x equals 3 and 0 are both in the domain. I'll show you just in a second why it's important. And changed the concavity of the function, the original function, right? Then x equals 0 and 3 are points of inflection or inflection points. Now, if you want to know where they are located, you need to take those 0 and 3 and plug them to the original function. And I want to do that for you to show you that we might ask you to do it as well. Because technically speaking, we do not find the points. X equals 0 and 3 are just inputs. So to find the points, plug x equals 0 and x equals 3 into original function, original f of x, which is x to the 4 minus 4x cubed. F at 0 is 0. F at 3 is, calculate carefully, 3 to the 4 minus 4 times 3 cubed, negative 27. So my points of inflections, points actually is supposed to have both input and output. So it should have x and y. It will be 0, 0 and 3, -27. That's much better answer, and sometimes we might ask you to find that, a couple for each. So the last step for these questions, this is kind of like last step over here, always plug into the original function. That's the idea. Finally, let's write down the intervals where the function is concave up and concave down. That's what we're gonna do for number 4. Let's do 4. So original function is concave up on, and then concave down on. Let's go to the sine line and use the sine line. Concave up, where the second derivative was positive. So from -infinity to 0, u is the notation for the union, from 3 to infinity. Concave down was between 0 and 3. Do not include the points of inflection, because there the second derivative was not positive and not negative. So why it's important that points of inflection are supposed to be in a domain? You will see sometimes that vertical asymptotes might change the concavity as well. The function can be concave up on the left and concave down on the right, just like 1 over x, for example. Well, this one is shifted. So this is not points of inflection, even though this point changed the concavity, because it's not in a domain, as the original function does not exist at this point. So that's just a note. Point should be in the domain. That's why I put it here, this note. Should be in a domain. Now let's look at the graph. I actually was hiding from you the result all this time. Here it is. And here's the graph, and check that we actually did the right thing. So we are saying that the function was supposed to look like a cup looking up from -infinity to 0. And indeed, this is the case. Look at this. From -infinity to 0, it is concave up. Then it's also concave up from 3, see, to plus infinity, concave up. So if the rain is falling onto this graph of the function, the water will accumulate. But from 0 to 3, you see, the water will fall down. Then this is where the function is concave down. The second derivative was positive or negative in that case. The second derivative was negative, so it's concave down. The second derivative was positive and positive, so it's concave up. Also, we found using second derivative test that at 3 we have local minimum. Remember the bottom of the smiley face, and we use second derivative to find that. At 0, it's not local minimum, local maximum, and later we actually find out that both are points of inflections. So that's very interesting. If you use first derivative test for 0, try yourself. Then you can see that for the first derivative, the sign of the first derivative will not change. And that's why at 0, there is no local maximum and no local minimum, because the original function was decreasing. At 0, stopped decreasing for a second and keep decreasing. So if the function is decreasing and then keep decreasing, this point is not local minimum or maximum. Very interesting point of view how to use second derivative, which shows us where the function is concave up, concave down, where the points of inflection happens, and how all of this can be used in so many different areas. Good job for watching such a long video. Now I'm pretty sure you're ready to be a professional in graphic functions, analyzing functions, and even getting a job, which actually pays you money for analysis of the function using calculus. Thank you for watching.